Tan H activation function. In the last few lectures, we were concentrating on sigmoid activation function, and we had seen that sigmoid activation has a drawback. What is the drawback? It is that it is not zero centered. So when it is not zero centered, we had seen that it is not a good option to use sigmoid in the hidden layers of your neural network. So automatically the next thing we are in search for is something which is zero centered. Sigmoid is not zero centered, but we want something which is zero centered. And the answer is tan H activation function. The tan H activation function, this is a zero centered activation function, and hence it rectifies this problem that you were having with sigmoid activation function. One thing, this is tan H, not just the normal tan that you are very familiar with. So what is the difference? This is coming from trigonometry. That is, when I say trigonometry, I meant circular trigonometry. That is, it is coming from the concept of different points on a circle. Instead, tan H, the hyperbolic tan, this is coming from hyperbolic trigonometry, or you can call hyperbolic geometry. What is tan H? That is tan hx. Tan hx, this can be written as sin hx divided by cos hx. So these all are hyperbolic geometry functions, not the circular trigonometry. Okay, let us get into this. We'll see what is tan hx and how can it be used as a good activation function, right? This is the point of this lecture. First thing, what is the requirement of an activation function? It is supposed to add non-linearity into your neural network. In your neural network, you will have many layers. Irrespective of the number of layers that you stack up, if you don't introduce this non-linearity, then it will be just a linear function. Whatever be the number of layers you stack up, it will still remain to be a very linear function. So if you want to model complex functions or complex models, you should have non-linearity in it. That is where activation function comes into picture. Okay, let us see what is tan H activation function, what is its formula, what is the logic behind it. All these things we are going to see. We'll first write the mathematical formula, then we'll explain logically. Okay, tan hx, tan h, it is tan h x. This can be expressed as e power x minus e power minus x divided by e power x plus e power minus x. This is the mathematical formula for tan H activation function. In case of sigmoid, what we had seen, in case of sigmoid of x, the formula was 1 by 1 plus e power minus x. So instead, if it is tan H, then this is the formula. Okay. Next thing is, what are the specialities of this tan H function? First of all, it is non-linear. That is very obvious because without that, you can't use it as an activation function at all. Over this, it is a smooth function. It is a differentiable function. These two are also very important because the graph should be smooth. It should be differentiable because whenever you want to do back propagation, you should be able to take the derivative, find out how much each neuron is contributing to the final loss, and accordingly you should be able to update the values of weights in that neuron. Okay, next thing is this is quite interesting. That is similar to the sigmoid function. Tan H is also having a sigmoid shape. What is sigmoid shape? It is the S shape. So then how is tan H different from sigmoid? I'll first show this in a graph, then it will be very evident for you. If this is your graph, your sigmoid function, it looked something like, I'll take a different color, let us say I'll take red. Sigmoid looked something like this. This is how your sigmoid function looked like, right? This is how it went. Instead, if it is tan H, so what are the values here? When I say this, this is 0 and this highest point of sigmoid, this is 1. Let us say there is -1 somewhere here. Okay. So sigmoid was actually taking values in the range 0 to 1 and it was having a sigmoid shape, and the central point, this was 0.5. This was the scenario with sigmoid activation function. I'll write sigmoid there. This is sigmoid of x. Okay, sigmoid activation function. Instead, if I'm using tan h, then what happens? Tan h is having the same sigmoid shape, but the difference is it is zero centered. So it starts from somewhere here, then it comes like this, it goes through the 0 and then it saturates at 1. This is tan h. So both tan h and sigmoid of x, I'll write tan here, this is tan h of x. Both tan h as well as sigmoid of x, both are sigmoid in shape. Sigmoid means S shape, that is it, okay? So both are having sigmoid shape, but in case of sigmoid function, it is taking values between 0 and 1. But in case of tan h, it is taking values between -1 and 1. So you understood that what is tan h doing? It is taking values from the real line -infinity to infinity, and it is squashing it to a value between -1 and 1. This is the speciality of tan h. In case of sigmoid, what it was doing? It was taking the same values, but it was putting it into 0 and 1. Instead, tan h is putting it into a range between -1 and 1, because of which it is 0 centered. I drew the graph first because from here, it is easier for you to understand. Even if someone asks you what is the range, what is domain, how is it 0 centered, if you have the graph in your mind, it is easier for you to explain because all the things will be picturized in your mind. That is why I had you the graph first. Next thing, let us understand more logically what values it is taking, when it is taking, and what is the derivative. Okay. So the first thing, if your x, that is the input, if your x is taking a very large positive value, then what happens? If your x is taking a very large positive value, then your tan h function, tan h of x, this will be very close to 1. In case of sigmoid also, this part was same. Whenever x is taking very large positive value, sigmoid also took value very close to 1. Tan h is also taking value very close to 1. Next thing is, if your x is a very large negative number, this is where the difference comes in. Here, your tan h of x, this will take a value which is very close to -1. So in case of sigmoid, this was taking a value very close to 0, but here it is taking a value very close to -1. Next thing is, what if x is 0? At x is equal to 0, at x is equal to 0, what happens? Your tan h of x, it will also take the value 0. So these things are actually evident from graph. If you have the graph in your mind, these things will automatically come to you. You'll automatically remember all these things if you have this graph in your mind. Okay. Next point is, we already talked that sigmoid is not 0 centered and tan h is 0 centered. So let us talk about this 0 centeredness next, because this is an important property because of which tan h is a better activation function than sigmoid. Okay. So what is this 0 centeredness? That basically means your positive and negative activations, these are going to be balanced around 0. That is, when your x is taking negative values, it will also give negative value. If x is taking positive value, tan h will also give positive value. So I wrote negative on this side, positive on this side. So whichever, this is negative, this is positive. So because of this, it is having 0 centered nature. And what is the advantage of the 0 centeredness? Your gradients will not always have the same sign. Because it is having different signs, you will have faster optimization. Your optimization algorithm will run faster. You will be able to hit the minima much faster than with another activation function which is having all gradients of same sign. This is the difference. Basically, you can say your gradients are not biased in this case. All those are not having same sign, right? Another thing you want to understand is, how is tan h taking values when your value of x changes? Let us say your value of x, if this is a very small value, for small values of x, tan h is almost the same as x. That is tan h of x. This takes almost the same value of x. See, this is only for very small values. But when your mode x increases. Why did I put mode? Because if it is positively increasing or negatively increasing, in both cases what happens, it saturates towards the upper point, that is -1 or 1, whichever it be. It saturates, and then one problem arises. This is called as vanishing gradient problem. This is what we had discussed in case of sigmoid function as well. In tan h also this issue will be present, because when the value of x is larger, whether it be positively larger or negatively larger, it will saturate towards 1 or -1, because of which vanishing gradient problem will still be there. So even if you use tan h, vanishing gradient problem will be there, but your zero centeredness, this issue is rectified because tan h is zero centered, unlike your sigmoid activation function. Okay. So the next important part is, when learning about an activation function, in the previous lectures also we discussed, very important part is to learn about gradients, because the core of an activation function is how its gradient behaves. Because what is the whole use of activation function? You did forward propagation, then during backward propagation, using the gradient of this activation function, you want to update weights in each neuron. This is why gradient and the behavior of this gradient is a core part for any activation function. So let us see how this gradient of tan h is behaving. Okay. First I'll tell you, if you take gradient, then d by dx of tan hx, this will give you 1 minus tan h square x. So I'm just writing this first so that you have this in mind when I'm doing the derivation. If you take gradient of tan h function, you will get 1 minus tan h square x. This is what you are going to get. Just keep this in mind. We are going to do complete derivation. I'm not going to simply tell you have to by heart. Instead, see, especially gradients and these things, it is good if it automatically comes to your mind when you learn this many times, or when you go through this many times. Automatically it will come to your mind that gradient of tan h is 1 minus tan h square x. But you should learn this by understanding how this is getting derived. Then only it will make logical sense for you. Otherwise, it will be simply by hearting different values, which is not good as a student. Okay. So you should understand how this is coming. Let us see how exactly this gradient is coming up. Okay. First thing, you already know gradient is largest near 0. In case of sigmoid, we had seen gradient was largest near 0, 0.5, because that was on which it was centered. Here it is 0 centered, so you will automatically expect, because it is same sigmoid shape, that around 0 you will get the largest gradient, which is true. And whenever your mode x is larger, that is on either of the sides, be it positive or negative, that is when your gradient vanishes. Okay, this at 0 you have the largest gradient, and in larger values of x, be it positively larger or negatively larger, you have smaller values of gradient. Okay, this is the scenario. Let us see how the gradient is derived, then the whole picture will be better clear for you. Okay, let us understand how gradient can be derived. First thing, we'll take this tan h function. What did we learn about tan h? Tan h of x, tan h, okay, this can be written as tan h of x is equal to, what did we learn? We learned at the beginning here, e power x minus e power minus x divided by e power x plus e power minus x. This is how you can express tan h. Okay, so I'm going to write that again here, e power x minus e power minus x divided by e power x plus e power minus x. This is the formula for tan h. What do you want to do? You want to take derivative. So when you think about derivative, you should think about what technique you should use in order to find the derivative. As soon as you see this, you can see this is in u by v form. This is in u by v form. And what did you learn in your 12th standard, maybe when you learned about differentiation? If it is in u by v form, how can you find the derivative? You can do u dash into v minus u into v dash divided by v square. This is the formula you can use in order to find the derivative whenever it is in u by v form. Okay, So what is u here? U will be the numerator, which is e power x minus e power minus x. And what about v? V is the denominator, which is e power x plus e power minus x. So this is your u, this is your v. Okay. Next step is you need u dash and v dash here. So let us find those values out. Then we'll start solving this. Your u dash will be d by dx of e power x minus e power minus x. So if you take derivative of e power x, you know you will get e power x itself. So there is nothing there. Minus, what about derivative of e power minus x? If you take derivative of e power minus x, you will get e power minus x into derivative of minus x, which is minus 1. So this minus and this minus cancels out. So I can write plus here. Okay. So this is the derivative of u. Next thing is v dash, derivative of v with respect to x. It will be d by dx of e power x plus e power minus x. What will I get here? If I do this, derivative of e power x, it's e power x itself, plus derivative of e power minus x is e power minus x into derivative of minus x, which is minus 1. So this minus sign I can put here, then it becomes e power x minus e power minus x. This is my derivative of v. Now it's time for us to find the derivative of tan hx. D by dx of tan hx. This can be written as, in this uv form I'm going to write this. So you can say u dash into v minus u into v dash whole divided by v square. So at this point I just have to substitute values of u dash, v dash, u and v. Okay, I can simply substitute from there. So what am I going to do? I am going to write this is equal to, what is u dash? U dash is this value. So e power x plus e power minus x plus e power minus x. Next term is v. So v I have here, it is again e power x plus e power minus x. So e power x plus e power minus x. Minus, next is u into v dash. What is u? U is my value here. This is u, e power x minus e power minus x. E power x minus e power minus x. Into, what is v dash? V dash value is here. It is also e power x minus e power minus x. E power x minus e power minus x. Whole divided by v square. What is the value of v? V is this, e power x plus e power minus x. So this will be e power x plus e power minus x the whole square. So this is the value that I got. Next thing is, how can I simplify this further? So if you see this, both these terms are same. So I can write as whole square. Okay, this divided by should be the, this is equal to e power x plus e power minus x the whole square minus e power x minus e power minus x the whole square whole divided by e power x plus e power minus x the whole square. This is the term that I got. Next thing is, if you see the numerator, this is in the form of a plus b the whole square minus a minus b the whole square. This is the form in which you can see this numerator. This numerator is in the form a plus b the whole square minus a minus b the whole square. If you simply solve this, what you will get is, this part will be a square plus 2ab plus b square minus the other part will be a square minus 2ab plus b square. Then what happens? This a square and this a square cancels out because there is a minus here. This b square and this b square cancels out because of the same reason there is a minus here. 2ab minus 2ab becomes 4ab. So effectively, a plus b whole square minus a minus b whole square, final answer is 4ab. So this thing, instead of writing this, you can simply write in 4ab form. What is a here? A is your e power x and b is your e power minus x. What I'm going to do is, I will remove this thing and instead of this, I'll write as 4ab, which will be 4 into a is e power x into e power minus x. Now if you see, e power minus x is 1 by e power x. So e power x into e power minus x, this will also get cancelled out. Effectively, this will simply by 4 divided by e power x plus e power minus x the whole square. This is what you got now. Next step. So what are we trying to do? We are going to find this out. Tan h derivative is 1 minus tan h square x. That is where we are going to reach. So as of now, we have this form. Think about this. Think how you can improve over this. What improvement can you do in order to take it to that best form? Okay, the form that we want. So next thing I'm going to do is I'll start with cos x. So we are going to do something with cos x here. What I will do is I'll just show you how this form has a relation with cos h. Okay. Your cos h x formula in the previous cos h lecture also we had discussed. This is e power x plus e power minus x whole divided by 2. This is your cos x. Cos hx, which means your e power x plus e power minus x, this can be written as 2 cos hx, right? This can also be right, which means this e power x plus e power minus x here, this can be substituted with 2 cos hx, right? So what I'll do is, instead of this, I'll put here 2 cos hx. This is also right. Then I can write this as 4 divided by 2 square is 4 cos h square x, which means the 4 and 4 will cancel out. This will be 1 by cos h square x. Now does it seem any familiar to you? 1 by cos h square x. Instead of 1 by cos h square, you can write sec h. Instead of 1 by cos, you can write sec h. So it will be sec h square x. Instead of writing 1 by cos h square x, you can write sec h square x. This is where one more thing. What is sec h square? Sec h square can also be written as 1 minus tan h square x. So you got the formula that you want, which is derivative of tan hx can be written as 1 minus tan h square x. So that is what we have derived here. You took tan hx, you took the derivative of tan hx, finally you reached 1 minus tan h square x. So this is what we wanted to find out. So at this point, you know what is the derivative of tan h. Let us go through what are the advantages and disadvantages. We already know few, but let us put all these together so that you're clear about it. First, about the advantages of tan h function. Tan h, if you are using as an activation function, you know it is zero centered. So the problem that was there with sigmoid activation function, that is rectified now. And the second big advantage is that it is having a smooth gradient. So whenever you want an activation function, you should have smooth gradient so that taking derivative is easy. Okay, that is why you have a smooth gradient here, which is an advantage with tan h activation function. And what about the disadvantages? We had already learned that it is having vanishing gradient problem, which is a disadvantage. One more thing you can say is, maybe you can say it is computationally expensive. So if you are, again, if you say in case of sigmoid, if you ask me e power x minus e power minus x divided by e power x plus e power minus x, whether this is very computationally expensive for modern computers, it may not be. But when you compare with ReLU or other activation functions, then this becomes a computationally expensive operation. Okay. So these are the major drawbacks with tan h. So you know, because of these positives, these advantages, tan h is a very good activation function. Next question automatically is, where is this tan h activation function used? If it is a useful function, then where are you going to use this tan h activation function? One main thing is we already know it is a good activation function for the hidden layers of a neural network, because of which it is used in recurrent neural networks, RNNs, then similarly long short-term memory, LSTMs, GRUs. So we'll learn about all these particular networks in the upcoming lectures. At that point, it will be clear for you what exactly are these networks. But for now, understand these are different types of neural networks. In all these, TANH is a very good activation function to be used. This is what you have to understand this. What is the reason? The reason is one bounded range, which is between -1 and 1. So this, how this helps is, this range actually helps you when it is used in these neural networks in order to control the values that are coming out in each layer. What happens is, if you actually use the real value instead of this scaled value into -1 and 1, what happens is when you have a lot of layers, these values may shoot up. If it's a large value here, again you used some function here and got even larger value. Finally, by the time it reaches output layer, value may shoot up to very large extent. This is where an activation function like TANH will help you to keep it in this range of -1 to 1. Okay. So you can say it will prevent those values from blowing up. This is what you can understand. Plus, obviously, it will add non-linearity. That is a very important part. So one more thing before we conclude this lecture, one more thing we'll mention. That is, let us say you want to find gradient of TANH. You have something like let us say z is equal to sum of all w into x, wj xj, something like this. This is your value in the neuron. And then you have activation function. Let us say activation is equal to TANH. So activation is equal to TANH of set. This is what you are using. If this is the scenario, then when you take derivative with respect to this z, what happens? Del L by del z. Okay, I'll take some space here. Your del L by del z, this can be written as del L by del A, the activation, into del A by del Z. This is how you will write. And with TANH, this del A by del Z, this can be directly written as 1 minus A square. Why? The derivative of TANH is 1 minus TANH square. That is why TANH function, you can directly write this as 1 minus A square. So this is how you can actually solve when you are using in neural networks. Okay. So this is it about TANH activation function. Mainly keep in mind that it is very similar to sigmoid. It is having the sigmoid shape as well, but it has an advantage that it is zero centered, and it will transform the incoming values, the real numbers, into a value between -1 and 1. This is what TANH does. Okay.